Okay, everybody. Well, thank you all for coming. I was afraid with the title, which sounds a bit difficult, that the hall will be half full. I tried to tell you next week it won't be difficult. Hopefully it'll be quite fun. So we'll get going in just a minute. Just to say the final lecture for this year is about searching for life in the universe. I'm nominally, supposedly, a world expert on this, in that I did actually take part and help run a 6-year project looking at 800 nearby stars to see if E.T. was phoning home, but he wasn't, sadly. There will be a transcript, but I was just going to say, sometime last year I was interviewed at Jodrell by somebody who said they were hoping to bring out a magazine, and something arrived in the post yesterday called Alien Times. And I think there's about 5 pages of me in there, so God help it. Anyway, at the very end, they actually sell our telescope off for £69 on the inside back page, you know, buy the Lovell telescope. So anyway, if you see that, ignore it. Right, okay, let's begin. This always happens, doesn't it, when I start, that it comes up with a virus scan. I want to start with Isaac Newton, because, of course, his theory of gravity was the one that has basically kept us going for a very long time. And apart from conditions where gravity is very strong, for example near the sun, it works very, very well. He was born in 1642 on Christmas Day. He was educated at the Free Grammar School at Grantham. In fact, he stayed with the headmaster who gave him tuition, and then went to Trinity College, Cambridge. But you may remember that around 65, 66, it was the time of the plague. And along with all the other students, he was sent home. He was sent down, as they say. And so he had to stay for a year or so helping his mother run the farm, which he didn't really like doing. But the great thing was that he spent a lot of his time thinking. And there's a story which is almost certainly apocryphal, that he was sitting under the apple tree in his garden, and an apple fell on him. That was good. And maybe at the same time, he could look up and see the moon in the sky, and wondered why the moon wasn't falling. And I think his great moment of genius was to realize that the moon was falling. In a book that he actually wrote for the general public, rather than his famous work Principia, he gave a lovely illustration. He had a diagram, a mountain coming out of on the Earth, very high mountain, so it was above the Earth's atmosphere, the top of it. On the top of this mountain, there was a cannon that fired a cannonball horizontal. And obviously, if you fire a cannonball, it will fly down, and it will sort of then land on the Earth, won't it? Can you see, if you increase the speed at which you fire the cannonball, it will go further before it lands? And if you kept on doing that faster and faster and faster, there'd come a point when it was travelling about 18,000 miles at the exit of the muzzle, it wouldn't actually reach the ground. It would go all the way around, and about an hour or so later it would hit you in the back of the head. Now, the point is this, that the falling of that cannonball was just at the right rate to keep it at the same distance above the surface of the Earth. Does that sound plausible? Well, he looked up at the moon, and he was able to calculate how much the moon would fall, or would have to fall, in a second, in order to keep a circular orbit around the Earth. From that, he was able to calculate the value of little g, the acceleration due to gravity, at the distance of the moon. And it turned out to be 1/3600th of that at the surface of the Earth. Now, he knew that the moon, sorry, wrong way, the moon was 60 times further away from the center of the Earth than was the Earth's surface. Does that give you a clue? At a distance of 60 times further away, gravity was 1/3600th. Can you see it's fallen as the square of the distance? Now, of course, that is only true if you could regard the whole of the Earth's mass as being concentrated at the center. And before he could publish his theory of gravity, he had to invent calculus, because that's the only way you can make that proof. He called it fluxions. When he'd done that, he was able then to say, yes, we can regard the whole of the Earth as if its mass is at the centre, and so we have 1r and 60r, it's goes as the inverse square. So he came up with his law of gravitation, where big G is in fact the constant, the universal constant of gravitation. He actually estimated that from, again, looking at the Moon's orbit, and got it pretty accurate. He had to know the mass of the Earth. He knew the size of the Earth. He knew the density of the ground, you know, that you were standing on, and he made an assumption that the average density of the Earth would be twice that of the surface density. Do you get the idea? And that was pretty much right. And so he got a good value for big G as well. Now, one thing I find interesting, he called it the law of universal gravitation. And the point, I think, is this. From his law, from this, it takes about half a page, you can actually derive Kepler's third law of planetary motion. That relates the distance of the planets from the Sun to the time it takes to go around. I mentioned that in the very first lecture some of you might have been at. Now, because that essentially was the whole of the universe that we knew about at that time, the solar system, he knew, therefore, that his theory applied to the whole of the then known universe. So I think that's why he felt happy to call it universal gravitation. Okay, so far. Shout at me when it gets hard, all right? That's what I've just said. There was only one problem that's actually ever been shown in our solar system where Newtonian theory doesn't quite work. It's in the orbit of Mercury. We say that it precesses. The axis, the major axis of the orbit, gradually goes round, as you see here, rather exaggerated. Does that remind you of spirographs? Because that's the same basic thing. And it isn't quite right. The amount by which it precesses, he does predict it will precess, but isn't quite right. So that was about the only weak spot. Well, now, of course, we come to Albert Einstein, which is what most of this lecture is about. As you know, he became a patent clerk, and that probably gave him some time to think as well. And in 1905, he had what I think I'd call his annus mirabilis. He produced, annus, if I said that right, he produced 3 papers. One was about Brownian motion, the cause of it. The second one was about the photoelectric effect, evidence for quantum theory, for which he got the Nobel Prize. But of course, the paper that we all think about with Einstein in 1905 was his paper, The Special Theory of Relativity. And a little bit later that year, he produced a supplementary paper relating energy to mass. Now, what do we need to know about the special theory of relativity? Well, we don't need to know very much. In fact, it's a jolly sight harder, in my view, to give a lecture about special relativity to an audience like yourselves than it is about general relativity. You actually have to do some sums. For general relativity, we don't. Well, he said that light travels through space at a constant speed. I've given you the value there, not you need to know it. It takes about 3 nanoseconds to travel a foot. He also said that no material thing or any information, nothing basically, can travel through space faster than the speed of light. Now, I've highlighted the word through. Why have I done that? Because there is nothing to say in his theory that 2 objects cannot go apart from each other faster than the speed of light, providing they are being carried by the expansion of space. Think about making a currant bun. You take some dough, you put some currants in it, fairly tightly packed unless you're a bit miserly, you put it into the oven, and hopefully after, it always was 20 minutes at number gas regular 4, but anyway, whatever it is, hopefully it comes out bigger, doesn't it? In which case those currants will be further apart than they were when you put them in the oven. Now, those currents have not moved through the dough, they have been carried apart by the expansion of the dough. In just the same way, once you get beyond our little local group of galaxies, which are gravitationally bound, all the other galaxies we see out there are being carried apart by the expansion of space. And very early on in the universe, just after the Big Bang, in fact, the universe was expanding. Space was expanding faster than the speed of light, and that, in fact, is going to be happening again in the future. So that's just an important thing, I think, to point out. Well, from his theory, you get a rather more complicated formula for when you try and summate two speeds, that if two things are going apart from each other at 3/4 the speed of light, they don't actually go apart from each other. They're both moving at 3/4 the speed of light. Sorry, their typical speed away from each other is not twice that, it's only 0.96. So as you get near the speed of light, it gets very difficult to make things get any bigger. Something that I think you've all heard of is called time dilation, and basically something that is moving, a clock that's moving quickly, goes more slowly than one that's actually moving at 0 speed on the ground, and that's going to come up again later. I happen to be a twin, and I sometimes vie with my twin brother as to which of us travels around the world on jet aircraft more often, in case we'll actually change our ages relative to each other, but it's not by much. So that's one thing we're going to come back to. The other thing is, which is a very hard thing to conceive, if you go very fast, your length contracts compared to something that's not actually moving. So if you actually buy a new car, which actually is too long for your garage, what you can do is to drive into it exceedingly quickly. In fact, if you're going at 0.866c, you can actually reduce its length by a half. The trouble is that when you hit the end here, it'll then stop and it will come out the back again. By the way, there's a lovely book called Mr. Tompkins in Wonderland. Has anybody ever read it or seen it? Isn't it? Would you agree? It's very good. George Gamow, I think I mentioned him, wonderful physicist. Basically, what happens is this, that Mr. Tompkins goes to some lectures, just like you're doing, and he falls asleep. And he has a dream, and in the dream, the things to do with relativity in this particular case, they get much more enhanced. So he can actually see, as a bicycle goes past him, it gets squashed. Then he wakes up, and in the back of the book, there are the transcripts of the actual talks. And that's how I learned all my special relativity, I tell you. You can buy it as Mr. Tompkins in paperback, and there's a new version that came out, a revised version more recently, but it is worth reading about it. So that's length contraction. And as you all know, of course, the relationship between mass and energy, E equals mc squared. Now, it was a long time before, 10 years before he produced what's called the general theory of relativity. And I just make a point down the bottom here. It's often wrongly called the theory of general relativity, as opposed to the general theory of relativity. But we often just reduce it to general relativity. So, it's a theory of gravity. And he realized there was a fundamental problem with Newton's theory. And let's do a thought experiment, one of two we're going to do. Let's consider what would happen if the sun suddenly disappeared. If I had a string and a ball on the end and I whirled it around, which I'm not allowed to do for various reasons, and I let go, what will happen to the ball? It'll fly off at a tangent, won't it? So what Newton's theory says, that if somehow the sun could suddenly disappear, the Earth would instantaneously fly off at a tangent. Now, can you see Einstein could see that couldn't be true? Because information about the fact that the sun has gone could not reach the Earth until about 8.3 minutes, the same time as it takes light to reach us. So, in fact, the Earth would fly off at a tangent at just the same moment that we would see the sun disappear. Do you see that? So, something has to tell the Earth that the sun has gone. The information must travel from where the sun was to the Earth to tell it it's no longer there. And so basically Einstein predicted the existence of what he called gravitational waves that carry information about changes in mass. So that's something we'll come back to a lot of, or several times. So that's exactly what I've said here. He predicted the existence of gravitational waves. In fact, if you apply Einstein's theory to Mercury, the correction you get is exactly right to sort it out. So it basically solved that particular problem. So that was the first, in a sense, test that his theory was on the right lines. Now, let's try and give you a feel, an understanding of what gravity is as understood by Einstein. In Einstein's view, in the absence of mass, we say that space is flat. And I hate that term because it implies it's two-dimensional. It isn't. What it means is that Euclidean geometry holds sway. And if you remember from school, if you draw a triangle on a flat sheet of paper, or in our case, if you make any large triangle in space, any orientation, the angles, the inscribed angles, add up to 180 degrees. Do you all remember that from school? And the other thing is that if we have two parallel laser beams, I must be careful where I point these, but if I hold them a metre apart, James, they're going above you. Well, if you turn round, you'll find that they're exactly the same. No, don't worry about it. I can't hold them very steady. But essentially, in flat space, two parallel light beams will remain parallel, like railway tracks ought to. Okay? So that's two things about flat space. I would like to call it Euclidean space. That's my own preferred term. I haven't quite had the courage to use that term solidly in a book that I'm just finishing, but not to worry. Someday we'll change it from being flat. Now, if you then put a mass into flat space, it makes the space locally curved. And if this was a flat rubber sheet, I could take a ball bearing, I could roll it across, and hopefully it would go in a straight line. That's a photon travelling through flat space. If you then put a lead ball somewhere on that rubber sheet, can you see it will form a depression just as you see there? And as a ball bearing gets near that depression, it will actually curve. If it goes to the right of that depression, it will curve that way. To the left, it'll curve that way. And that is, in fact, in some sense, making the direction of the rays of light change direction, which is what a lens does. So this is called a gravitational lens. In positively curved space, as a matter of interest, the inscribed angles add up to more than 180 degrees, and your two parallel laser beams will actually converge. So that's what I've just said. And that's quite a nice example. And if this were the sun, and this were a star, it implies, that were a star, it implies that the direction that we see a star close to the sun would not, in fact, be the same as if the sun wasn't there, because the path of the light from that star has actually curved, making us think the star is there. So essentially, stars very close to the sun will appear to be a little further away. It's at 1.75 arc seconds, which isn't an awful lot. But this, of course, gave a method of testing Einstein's theory. We'll come to that very shortly. Let me try and explain what gravity is. In Einstein's view, our Earth is going around the sun simply because that's what things do in curved space. There's no force being applied to it. It just thinks it's going in a straight line. Gravity, and I'm sorry it's not showing up very well, it's a force that we infer, we make it up to explain what happens in a curved three-dimensional space if we believe or assume that the space is flat. Now, let me try and give you a little analogy, which is a bit strange, but it's quite fun. Could you imagine a world where all the inhabitants who only live in the southern hemisphere believe that the surface of their world is flat? They're members of the Flat Earth Society. The northern half of the planet, that's from the equator up to the North Pole, is covered, let's say, with a totally frictionless surface. Ice, but better than ice. Well, two intrepid explorers decide they want to explore this part of the world that they've never been to. And they get two little rocket sledge type things, and they start 10 kilometers apart, pointing due north. They fire their rockets so they travel at precisely the same speed, and they leave the equator at precisely the same time. Can you see they will believe they will travel over the ice keeping 10 kilometers apart? Because they think that space is flat. They will therefore be somewhat upset and possibly hurt when they arrive at the North Pole and collide. Now, this will worry them. Whether the AA reaches there, I don't know, but it will worry them. And they'll say, well, look, we shouldn't have done this. If the space is flat, we should have kept 10 kilometers apart. And the only way they could actually rationally explain why they collided is that there must be some force that's attracting their two sledges together. And so brought them together at that particular time. And they might give that force, quotes, a name, gravity. Do you see? They are making up a force, gravity, to explain what happens on a positively curved surface if they assume it isn't curved but flat. Does that work, that analogy? So that's really what's going on. We think we live in flat space because we can't see the fact it's curved, and we have to make up gravity to explain what we see happen. So how can we try and test Einstein's predictions? Well, I made the point about a star very close to the sun would not appear in the same position. Now, of course, you can't see stars close to the sun very often, only at a time of a total eclipse. And there was going to be one in 1919, when rather nicely the sun was going to be in front of the Hyades cluster, which is in Taurus, and there are lots of stars. That's good. Lots of quite bright stars. So what do? You take a telescope, you take a photograph with it, because it's important it's the same telescope, of the Hyades cluster when you can still see it. Can you see that's going to be some time before? Because you can only do that when it's dark. Then you wait for the eclipse, and you take identical photographs during totality, when hopefully you'll be able to see the stars. And this is what Sir Arthur Eddington did. Do you remember I mentioned him last week? He's a very clever guy, he really was. In fact, Einstein quite seriously said he probably understood relativity better than Einstein did. And I told you this little quote, if you weren't here last time, I'll just quickly repeat it. Someone said to Eddington, I believe you're one of only 3 people in the world that understand Einstein's theory of relativity, of general relativity. He said, I'm not sure who the other one is. Obviously, one was Einstein. He couldn't think of anybody else. So he was very clever. So he carried out this experiment. He took telescopes to a place called Sobral, which is up here in South America, and colleagues went to an island called Principe off Africa, and you can see the eclipse track. And this is just indicating the stars that should basically shift away. And this actually shows the Sobral antenna. The telescopes were in here, 2 telescopes looking up past the sun. Well, they brought the plates home and they measured them. Unfortunately, one of the telescopes didn't really produce very good images. It may have been a temperature problem. So they sort of had to discard those, and they had to actually take the images taken by the smaller telescope, which weren't quite as precise. However, a telescope here at Principe was pretty good. And they basically announced that the observations did agree with Einstein's theory. People who've looked at the observations since then have some doubts. He perhaps threw away any of the observations that didn't quite fit, and he included those that he gave more weight to those that did, which isn't the best of scientific method. So it was, I've word the word dubious there. I think it was just about okay, but really rather marginal. However, in 1922, there was an eclipse visible in Australia, and a team from Lick Observatory went, and the head of that team did not like Einstein's theory. He wanted to prove that relativity was wrong, but they got excellent results that showed that it, in fact, was right. It did agree. Now, if you've got someone who tries to disprove something and can't, do you agree you tend to accept his results? It's certainly true in all fields, I'm afraid to say, that quite subconsciously sometimes, one tends to push the results in the direction that you're hoping that they should go. And it does certainly happen in all sorts of fields, and often not intentionally. Anyway, by 1922, this particular experiment, I think, showed that Einstein was right, but not to great accuracy. More recently, we've had some nice observations by the Hipparcos satellite. Now, I mentioned earlier that close to the Sun, the deflection is 1.75 arc seconds. That's actually not easy to measure because star images tend to be an arc second or so across, just because of the atmosphere. But if you're out in space, can you see your images are better? And obviously you can't look, except during a total eclipse, at what's happening close to the Sun, but the effect is still 4 milliarc seconds, even at 90 degrees away. So it is possible to do these measurements with observations from space. And the Hipparcos satellite, they've analyzed 2 sets of data, and if Einstein's correct, this value should be 1. They've got 1.000 plus or minus 0.004, or 0.992 plus or minus 0.005. So that's pretty good, and those are the best optical observations of the deflection that we have. Radio observations are a bit better. I'm being modest here. In fact, whereas optical telescopes might possibly get to a millisecond, probably 10 milliseconds, we can do about 100 times better, largely because there's no atmosphere to worry about. We don't have the atmosphere to contend with. And we have arrays of telescopes that stretch all the way across Europe. And in 1995, they got 0.9996 plus or minus 0.00017. And in 2004, more recently, an analysis of 2 million observations taken by this network of telescopes gave 0.99992 plus or minus 0.00023. Would you agree that's getting pretty good? So the deflection of light as it travels through curved space, I should perhaps say space-time, but we'll use the word space, is getting fairly well accepted. And that's just a summary of these deflection results here, coming right down to, these were the optical ones all over the place, really. Radio got better and better, and then these VLBI observations. But along with Hipparcos, that's optical, that's done pretty well. So that's all been getting better. Now, there's another test that was thought up by someone called Erwin Shapiro in 1964. And this probably is the one that's given us the best value or the best precision to date. And I'd just like to do a bit of an experiment if I can. There's a gentleman through the door with a lovely white beard, sir. Could you pretend to be the planet Mars? All right? Now, I'm the haystack antenna, which is quite big, and you can see I fit that quite well. This is my radar antenna, and I send a radar beam to Mars, and it reflects off the surface of Mars and comes back to me. And I can calculate, because I know the orbit of Mars very accurately, precisely how long that will take. Does that sound plausible? I get some value. Now, I don't know if I could get someone to move across into the, about halfway across. Could the lady there, would you mind just standing in the middle? Yeah, please, thank you very much. Now, if we're looking at Mars, every so often Mars goes behind the Sun, or very close to it. And do you mind being the Sun? Your lovely head is the Sun. Now look, if I send a radar beam, and I'm getting here, because I've always got to be I'm now pointing my radar beam straight at Mars. Would you agree, sir? It's pointing straight at you. Would it reach Mars? No, it wouldn't, because as it goes past the Sun, it's going to curve round to the left. Do you see that? And it will sort of go, there's a gentleman standing there by the back. It might hit you. So it will then not come back, well, it won't do the right thing. In order to get a radar beam to Mars, it will just be lost in space. I've actually got to send my beam a bit to the right, so when it curves past the Sun, can you see it will reach Mars, and then it will come back along the same path. Does that sound reasonable? And that introduces a delay, which is called the Shapiro delay, and goes up to about 200 microseconds. Thank you so much. I do apologize for, but it was very helpful. Now, that is what, in fact, we see. And this is a sort of simulation. There's the Earth, there's Mars. And as the radar path goes close to the Sun, we get an excess time which is just under 200 microseconds. And you can measure that relatively accurately. The trouble with radar, two things. One is you're not quite sure which bit of Mars you're hitting. Can you see Mars isn't smooth? So that's one problem. And secondly, as you go very close to the Sun, you might remember the Sun has this lovely solar corona from last lecture. The radar waves go through that, and that actually slows things down a bit as well. So that's a slight problem. So that's the Shapiro delay. It's been done better over time by basically sending a signal to a spacecraft and then basically getting it sent back again. It's sort of an active radar. It was done with Mariner 6 and 7 when they were at Mars, and they got just 4 microseconds out from Einstein's prediction, which is pretty good. And this is in fact the Mariner data. Can you see this little peak coming up to just over 190 microseconds and then dropping down? So that's what happened as the path length from Mariner 6 went very close to the Sun. They also used the Viking landers to do the same trick, and they got it down to 0.1%. And most recently, do you know there's a lovely spacecraft, or there's a spacecraft called Cassini that's sending up wonderful pictures of Saturn? Well, they've done the same trick with that, using 2 frequencies, and that's important because they can then correct for the corona, because the different frequencies are affected in different ways, and they can solve for the corona. And they've now got it down to 1 part in 10 to the 5th, and that's pretty damn good. So this is probably one of the 2 best tests to date of any of Einstein's predictions. And this is just showing you the Shapiro delay results, Viking, Voyager, Cassini. It doesn't include one result which we got last year at Jodrell Bank, which I'll mention a bit later on. Now, what I do need to tell you about, because it's relevant to something in a minute or two, is called gravitational time dilation, which sounds horrible. It was first tested by Pound and Rebecca way back in '59. The point is this: Einstein's theory says that a clock in a strong gravitational field runs more slowly than the same clock would run in a lower gravitational field. That is, clocks on the moon will actually run more quickly, go fast, compared to clocks on the Earth, because the gravity there is less. And basically they had a clock, a sort of an atomic clock thing, a bit special, in the basement, and they sent it up to the top of that tower, and they actually agreed with Einstein to 10%, but it's been done far better since then. In 1976, a Scout rocket was actually sent up to a height of 10,000 kilometers carrying an atomic clock. And they monitored all of its observations during the time, and they actually got it to an agreement of 4.5 parts in 10 to the 10, agreeing to prediction to within 0.01%. So that's quite a nice verification. And the reason I want you to know that one is because I want to say something about relativity in action. You've all heard of the global positioning system that we use to send our cars down green roads and tracks and through fords. I've been sent down a green road, and it got so narrow, the only way out was to carry on. And we made it. And you see all these things in the papers, don't you, about it? Well, how does it work? That's what we need to know. This is probably not to scale, but there are a constellation of satellites in orbit around the Earth, and they carry transmitters and atomic clocks. Now, let's try and give you an idea of what's going on. Supposing there was one spacecraft here, and every second, precisely on the second, it doesn't work quite like this, but this is the right idea. Can you see it produces a pulse? It just produces a short pulse. Now, we're on the ground, we're here, and we have an atomic clock, so we've got the same time standard. Can you see we can then measure how long it takes the pulse to leave here and reach us? Okay, we know it was sent on the second. Oh, sorry. That's the second. Our clock tells us this is when the second sent at the same time left the spacecraft. That's the time t. We know, therefore, we're on the surface of a sphere whose radius is ct. Is that all right? And that will intersect the surface of the Earth, I think, hopefully, in a circle. So we know we're on that circle. Is that okay for everybody? Right. If we have a second spacecraft doing the same thing, then it would have another circle, and in fact, you'd either be here or there. Do you see that? Now, in fact, one of my GPSs, one of my early ones, when you started it up, it wanted to know where in the world you were. Has anyone ever seen that? Which country? And I think that's so it could actually solve from there or there. Anyway, so two clocks, two of these, with an atomic clock, would actually tell you where you were. But atomic clocks are a bit expensive, so we don't really want to do that. If you have 3 satellites, you can actually solve for time. You don't need to have an atomic clock. And that tells you where you are in 2 dimensions. So where you are on the ground, which is really what you want to know. And if you've actually got 4 satellites, you can give your position, but also your height. Now, typically, with the 28 satellites in orbit, there might be 8 or more visible at any one time. So you can actually do quite well. And my current GPS handheld one gets me to about 20 feet. The height isn't usually as good, but within perhaps 50 feet, you know what your height is. Is that all right? That's how GPS basically works. Now, you have to be a bit careful, because those satellites are moving around the Earth, aren't they? At fairly high speed, 20,000 miles an hour-ish. And that means, because of Einstein's special theory of relativity, that they're going to run slow, right? And it's about 7 microseconds a day. However, because they're a few hundred kilometers above the Earth, they're in a weaker gravitational field, and Einstein's general theory says they're going to run faster by 45 microseconds per day. So the net result is that there's a 38 microsecond per day difference. Can you see? So what you have to do is, on the ground, you have to set these clocks 38 microseconds slow, so that when they get into orbit, they're running at the right speed. Do you see that? And if you don't do that, you'd be in error by 10 kilometers after just one day of, of having them up there. So it is quite important. And I believe this is the only case where both special and general relativity actually have a bearing on things that work or don't work. So that's interesting. So that's GPS. It's obviously not a proof of Einstein's general theory or special theory. It's a nice demonstration. Okay, I mentioned this briefly, but way back in '72, our telescope at Jodrell Bank discovered what's called the Double Quasar. And I won't want to spend much more time on this, except to say that what we observed were 2 images of a distant quasar, and here was a foreground galaxy. And the point is that this was looking at the galaxy directly, and here we were seeing, this is looking at the quasar directly, and here we're seeing the quasar where the light has come down, and the radio waves have come down past the galaxy. Can you see they'd curve in the curved space and have come up? So we actually see the same object twice. So these are identical twins in space. But I said last time, I don't want to repeat it all, that because, can you see the path going down and up is longer than the direct path? We see the thing at 2 different times in existence, 417 days apart, and this gives actually a way of us measuring the scale factor of the universe. A nice application is if the galaxy is precisely in front of the distant quasar. In that case, the light from the quasar gets bent all the way round and gives a halo to the galaxy. So it's called an Einstein Ring. This is the Hubble image of an Einstein Ring. Now, it is just about bright enough. It's always very light in here. But this is a wonderful cluster. And here is a giant galaxy. There's lots of galaxies in this cluster. Can you see these arcs? Can you see the little curved arcs there? Beyond this cluster is another cluster of galaxies about twice as far away. And the light from those is being stretched out. And so the whole cluster of galaxies, the Abel cluster, is acting as a giant gravitational lens. And this is actually one way to see fainter objects, because you know lenses often can gather more light. You can see fainter objects through a telescope. In the same way, this technique is enabling some of the most distant objects in the universe to be imaged. So it really does work, I promise you. A very nice example, and next year I'll give a talk looking at the discovery of extrasolar planets, and a particular technique that was proposed about 12 years ago by one of our professors basically points out that if light from a distant star comes close to a foreground star, it too will act as a lens. And it will brighten the image of the distant star. And this is in fact an actual curve here, where the brightness is going up by about 7 times. How much you get an increase in brightness depends on how close the background star comes to the foreground star. And if it's very close, it's almost a factor of 10, which is a couple of magnitudes or so. So a star suddenly brightens. Well, it takes actually about 30 days to come and go, but it increases and decreases. And we now have telescopes all around the world that are continuously looking at great numbers of stars, great star fields, looking for any increase in the brightness. I'll just go back to this one, here and here and here. Now look, can you see how there are far more points there? The point is that having seen these few points, they said, look, this looks as though it's going up. So then they will get every telescope around the world to keep a continuous monitor. And that's what they're doing here. Now, this could be, it went close to the sun or something, so you couldn't see it. But then here, again, 3 different systems are looking at it to try and get the curve. So there's a continuous monitoring. Different parts of the sky are monitored by different telescopes. When they find something beginning to climb its brightness, everybody will look. And the point about this is a fun thing. If there happens to be a planet close to that star, then we might get a little baby blip from that. It can gravitationally microlens as well. And here is some real data. Again, they were looking at something, and they saw it going up, so they got a very, almost a continuous set of observations. And here, just over a couple of days, they've got this extra blip. And from that, they were able to deduce that that star has got a 5 Earth mass planet in orbit around it. Almost certainly the smallest planet that's ever been discovered. And only about 2 weeks ago, one of my colleagues and others in the UK discovered a smaller version of the solar system. Did anybody see that in the papers? It got in a fair number of papers, just so I'm not waffling. It is true. And basically, it's a system which has a Jupiter and a Saturn-like planet. It's a smaller star. They're slightly smaller planets. The scale's smaller. It's like a sort of a 2/3 version of our solar system. So there could well be some smaller planets there as well. So gravitational microlensing, the effect of the distortion of space-time by mass, is actually a way to discover small planets. Well, the final topic, really, gravitational waves. I mentioned those at the very beginning. How can we get gravitational waves? You only get gravitational waves produced when a mass distribution is changing. So our sun is not producing gravitational waves. It's rotating, but basically its center of mass is basically staying the same. A very nice analogy of producing gravitational waves, if you could imagine this as a still pond, and if I take, this is going to be the sun, the tip of this is a stick, and I rotate it because the sun's going around. If I do that and I keep it fixed, can you see it's not really going to make any waves? However, star systems can make waves. This is Cygnus the Swan, and I don't know how many of you actually observe the heavens, but the star called Albireo, which is the head of the Swan, is in fact a lovely double star system. 2 pictures, and that's perhaps a little impression of what it looks like. There's a lovely colour contrast. One is sort of a golden colour, and the other is a blue. So here we have 2 stars co-rotating. Another one I actually looked at the other night testing a telescope. They're much closer together. They're both white. It's the star Castor in Gemini. And here you can see a rather nice picture, 2 pictures of Castor. Now, here you've got two stars, can you see, going around each other? If I put two sticks like this, and this is water, and I rotate them, can you see that would cause a little ripple to travel out? And I hope the next one will give a little simulation of that. Do you get the idea? So two co-rotating masses will give rise to gravitational waves. They are very, very, very weak, but they are there. Our sun is currently, in its core, converting hydrogen to helium. At the end of its life, it will actually carry on from helium, through carbon, through oxygen, up to perhaps silicon. That's as far as it goes. But more massive stars can finish up with a core made up of iron. When the core's made of iron, that's the most stable nucleus, you can't get any more energy out. So gravity makes it collapse. What happens depends upon the mass of the core. If it's not more than about 1.4 solar masses, something like that, then finally it will actually remain as what's called a neutron star. If it's more massive than that, it actually collapses into what is called a black hole. What is a black hole? Very quickly, if I take a ball, I throw it up in the air, it will come back. If I did it faster and faster and faster, eventually, at 25,000 miles an hour, 11 kilometers per second, can you see the ball would escape? The escape velocity of the Earth. Can you see if I made the Earth more massive, more and more mass into the volume of the Earth, the escape velocity would go up? Greater gravitational pull. If I kept on doing that, there would come a point when the escape velocity was greater than the velocity of light. And then the Earth would actually become a black hole. You can also do that by compressing the Earth, and when the Earth gets to about 3 centimeters diameter, it would become a black hole. Now, black holes can have any size. We only know currently of two basic sizes. There are what are called supermassive black holes at the heart of galaxies, perhaps 1 billion solar masses. But some of the giant, the largest stars, they produce black holes. Way back in 1976, with one or two of my colleagues, we actually discovered where one of these was. It's in the constellation Monoceros. We didn't know it was a black hole then. It was still very, very exciting. I have some proof in that. This was in August 1975. I think my youngest son was born in May 1976. Anyway, there are about 12 or somewhat more remnants of stars that we know are black holes. There also can be tiny ones. You might have just seen in the papers a slight worry that when the Large Hadron Collider, you know, CERN, comes into operation, it could make a black hole which could then gobble up the whole of the Earth. Have you read that? Well, don't worry. They had to carry out a risk assessment, and I'm told it's not likely to happen. In fact, there's very good reason to believe it won't happen. But it probably could produce little micro black holes which evaporate very quickly. Now, that's coming on stream this year. I'm hoping we'll have some results from it by next year. And what it's probing are the conditions very close to the Big Bang. So I'm hoping next year, sometime either the last part of next year's series or the beginning of the one after, to give you a talk all about that and the Big Bang when we've got some results. It should be very exciting. That's always assuming we're still here. So that's the Large Hadron Collider. We do know of neutron stars. There's one here in what's called the Crab Nebula, a supernova that was seen to explode in 1054. And I talked in 2 lectures ago about the Double Pulsar, 2 neutron stars co-rotating. Now, there are 2 things about this. A, they are producing gravitational waves, but also, by pure chance, they actually happen to be rotating like this in the plane of us. Can you see it means that one of these is either behind that one or that one's behind this one? So the pulses actually have to come very close, and we get a very accurate Shapiro Delay measurement. We've got 0.05%, which I think is the most accurate test of Einstein's theories to date. Very close to the Cassini one. I wouldn't like to argue which is better. So that's good. What I really want to talk about is the effect of the gravitational waves. Now, this is the very end game. Because these 2 things are radiating, we believe, gravitational waves, energy is being lost. That energy has to come from somewhere, and it comes by the fact that these 2 objects should gradually, according to Einstein's predictions, get closer together. And the theory is that that should be 7 millimeters per day. And that is precisely what we measure. Because these are superb clocks, we can measure the orbit very, very precisely. This is the best test bed of Einstein's theories that's yet been discovered. So can you see, if they keep on gradually getting closer together, at an increasing rate actually, the nearer they get, they'll eventually coalesce into one. Well, this is what sort of would happen then. Here they are. I think I showed you this a couple of times ago, but I want to stress something different this time. Here they are in their final death throes. When they finally coalesce, two things happen. One is that you get what I can only call a gravitational wave tsunami, this big wave that goes out, but also you get a massive burst of what are called gamma rays. So there are gravitational waves, big burst of gravitational radiation, we believe, and also a burst of gamma rays. Now, that actually is interesting. The strength predicted of the coalescing of either two neutron stars or a black hole, a neutron star, whatever, should be sufficient for the world's current gravitational wave detectors to be able to detect. This is one called LIGO. Actually, there are two of these in America. We've got some in Europe as well. Now, let me try and explain how they work. I tried yesterday to buy some little boats, and I couldn't find any. You know the boats you put in bars for kiddies? I couldn't find any in our town of Macclesfield, so I've just got these. But can you imagine this is a boat there, and there's another boat here. This is on the sea. I want to make a tsunami detector. I haven't patented it, but this is the idea. Now, this is a flat sea, and a tsunami, which is a wave, comes along this way, and those what have been in boats, I think, know that when a wave reaches you, you do a bit of a circular motion. Would anybody agree that's the case? Someone's nodding. So you get a circular motion. If I had a laser on that boat and a mirror on this one, could you see I could measure the separation? And it should therefore have a little bit of a blip. Fair comment? A bit later, that will go back to where it was, and this one here will do the same trick, and that will have a blip too. So that will tell me two things. One, that there is a tsunami coming across the sea, but also how fast it's going. Quite useful. Okay, now there is a subtle problem with this, that what happens if a tsunami comes in this direction? Can you see both boats will do this together, and their separation will not change? Do you see that? They'll both be, I can't reach that one. They'll both do that together. So this bit won't change. So what you have to do, really, if you're going to be sensitive to all directions, is to have another boat, which is at right angles to this one. Can you see? So no matter what direction it comes from, you'll still detect it. Does that sound at least plausible? Right, well, this is exactly what's happening here. In a vacuum, a very good vacuum, 4 kilometers apart are two copper cylinders. There's a mirror on both of them, and a laser beam goes back and forth, and it measures the distance between them very accurately. And you can just see here, this is where one cylinder there, one cylinder there. Can you see there's a tube this way, which is that one, and there's one that way. So we have two at right angles. And these should be sensitive enough to detect the coalescence of two of these neutron stars within a distance of about 30 million light years. Now, that includes our local group of galaxies, which are typically 2 to 3 million light years away, but also some nearby groups such as those in Leo and Ursa Major. All right, so we're sensitive now to this happening over quite a large area. They have just literally, a couple of weeks ago, finished their final run of the first phase of LIGO. They've only actually published one paper. But it's quite interesting, because a year ago, there was a gamma ray burst. Remember I talked about these gamma rays? Observed in the direction about here, actually, of Andromeda, and it was thought this might be a coalescing neutron star pair in Andromeda Galaxy, right? Had that been the case, then the interferometers, of which 3 were running, 3 of these gravitational wave detectors were running at that time, they should have detected it, and they didn't. So that was a negative result, but it does imply that whatever it was that produced the gamma ray burst had to be much, much further away. Do you get the idea? Okay, now, they're not running at the moment because they're making enhanced LIGO, they're improving it, and then later, so it'll run again in a year's time, and later on they're going to make advanced. Enhanced is being done now. It will double the volume, sorry, double the area, double the distance, make the volume increase by 8, and then they're going to actually increase the radius of detection by 10, increasing the volume of space by 100. And that will happen about 2014. By that time, we jolly well ought to have detected a gravitational wave directly. Our experiments and others have shown that they must be there, but somebody sometime is going to detect one. It could happen. It won't happen this year because they're rebuilding them, but next year it could. And maybe, if I'm lucky, I'll be able to tell you about it whilst I'm still your professor of astronomy. I'd like to do that. Somewhere around 2015-16, we hope to have a gravitational wave detector in space. In fact, there are 3 systems, so you've actually got 1, 2, 3 arms to it. They're putting up a test system in 2009. This ought to go up at about 2016. And that, in fact, will be sensitive enough to detect these things happening across quite a lot of the universe. And you'll be getting detections, you know, several a day. So the era of gravitational wave astronomy hasn't quite begun yet, but we're very, very close. So as I said a minute ago, hopefully sometime soon someone will get a Nobel Prize for the direct detection of gravitational waves. I sincerely hope I'll be able to tell you about it while I'm still with you. Thank you for listening.